Good afternoon. Do you hear me? Okay, good. So let's begin our practice. So now we will begin new practice session, exercise session 4. And here you can see the main topics are finding eigenvalues and the singular values of matrices. Okay, so we have a command egg to find eigenvalues. So here you have two matrices, A1 and A2. And then for this matrices, and here is 100. So its size 100 by 100. So we need to find the eigenvalue for A1 and A2 eigenvalues, and then do small perturbation here. So for A1 and A2 in last row, we will add this kind of perturbation, epsilon. You can see here, epsilon, to the last row elements. And then you need to find the new eigenvalues for new perturbated matrices. Is it clear? So first of all, just find for this kind of matrices, and then eigenvalues, and find the eigenvalues for perturbated matrices. So you need to hurry up. We have here 10 exercises, and we have one more practice. So except this one. So that's why let me show already comments for you, which I did during the last with previous groups. Okay, so here, let me share. Okay, now here you can see editor. So, and in this editor we will work. So this is first exercise. So here n is 100, and we will construct p vector, which components are n till 1. So decreasing order, yes, because here you can see n till 1. This is. Do you understand me why we just create this p matrix here? And then we will work with this p matrix, because you can see here, this is n minus 1, n minus 1, n minus 2, and etc. till 1. Or here beginning from 0, n minus 2, n minus 2, and 1 till. And in this case, you can see n, n minus 1, n minus 2, etc. And n minus 1, n minus 1, n minus 2, n minus 2, n minus 2, three times here. And the 4 times here will be n minus 3, n minus 3, n minus 3, and then n minus 4, etc. You can see we'll continue till 1 here again. So we will build our matrices using p vector. Okay, so now here we will use this kind of commands: p, once, and one and all columns. You know what is it? So it generates. So it repeats n times the vector p and unit matrix whose n's row are all equal to the p vector. So this is just creating our new matrix now, and the work with this matrix. So here, diag once n minus 1, 1 minus 1. This is here we will find subdiagonal elements by this command. This is subdiagonal elements. Are all other elements are 0 except the first subdiagonal elements, which is equals to 1. And now next one, 3u. With command 3u, we will build upper triangular matrix here. Upper triangular matrix A and minus 1. So it's again, so you can see here, it should be 0 other elements. You can see here, yes? So other element in this case are zeros by this way. Is it clear? So, and now we need to build this kind of A1 matrix. So now let's continue. And here So this is with 3U we will do it. So, and now let's build our A1 matrix with these 3 comments. So A1, 3U, this is upper triangular matrix, the first subdiagonal, and the 3U, P, once and one, this comment we will use now, repeats n times vector P and minus subdiagonal, you can see here, diag, once and minus 1, 1, minus 1 subdiagonal, and one more subdiagonal here. So by this way, we will build our A1 matrix. So this is our A1 matrix. And now, for example, you can do it for n is 5 to show how it will be, for example. Yes, let me just try to do it for n is 5 here. So n is 5, you can see, and the P matrix we will build here. So P matrix, it's equals to this number. And now this vector, P vector, and now we will do this kind of matrix now. First of all, let's show this comment. What is it? Let me show. So you can see here, we will repeat this P vector for all rows, 5, 4, 3, 2, 1, 5, 4, 3, 2, 1, etc. And then using this diag, what can we do here? Just doing subdiagonal matrix. You can see 1, 1, 1, 1. This is subdiagonal and other elements are zeros here. And the 3UA minus 1, what is it? But here we don't have A. So that's why let's do this one, 3U, this one, and show here. Just a second. So here we have one error, small error here we have. So let me just write one more time. So here you can see 3U with parentheses. So I think, so yes, now it's correct. Now you can see here our matrix, 5 by 5 matrix. Yes, 5, 4, 3, 2, 1, 4, 4, 3, 2, 1, and then 3, 3, 2, 1, 2, 2, 1, and 1, 1. We need to build such kind of matrix for 100. You can see here. So this is for 100, A1. And now we will do in generally, okay, using these comments. And then we need to find our eigenvalues of exact matrix A1. So here we will do outputs S1 vector. This is eigenvector and lambda 1, and values of lambda and we will use this command eig. So here using this command, we can find eigenvalues of our A1 matrix. And now we will do perturbation. So we need to do perturbation. Here you can see A1P is equals to A1 now as initial value. And then we will change our A1P and all columns. You can see here we need to add to the last row here. Yes? To the last row elements of both matrices. So do this perturbation. So we will just add to the nth row of our A1P, which means perturbated matrix. So just add this value, epsilon, and here we will find now new lambda 1P. And so here again we will use the command eig. So to find the new eigenvalues of perturbated matrix, and then find error between them, between this first eigenvalues and the second eigenvalues. How? Here we will use this command sort. It will sort in order to decreasing here in this case. So absolute value sort diag lambda 1 minus sort lambda 1P. So we will just find difference between them. And we will define conditioning also, K1, conditioning of this matrix S1. And we'll find the norm. So M1, which gives us K1 times norm of this matrix, the difference of two matrices. And then consider the graph of our lambda, so our eigenvalues. Here you can see real lambda. This is real part of lambda and imagined part of lambda. It can be complex number also. So here you can see now R asterisk, so it means red stars. We will denote it with red stars. And here you can see for this second perturbated matrix, and here we will denote it KO, so black circles. Okay, this problem is ill-conditioned. We will now just run this program. How to run it? So here we will just select. You can do selection and just enter F9, or here you can see in your menu run selection, for example, or you can just save this file and run. Doesn't matter. You can do with selection or without selection, doing saving file and run it. Okay, so we just run this selection, and in your command window, now you obtain result here. So you can see here K1 is equals to 5.6438. So it means this is ill-conditioned problem because it's so far from 1. And so it means small perturbation to our matrix leads a large perturbation of the eigenvalues. So this is ill-conditioned problem, that's why. And here you can see now the value of M1 also, this normalized value. Now we need to consider our graph also. Here you can see our graph. So red stars was eigenvalues for exact matrix, given matrix A1, and black circles, they are eigenvalues of perturbated matrix. Here you can see, however, we have size 100 by 100. We have 100 eigenvalues here. Is it clear, students? Any questions here? So this is comment of our exercise. And now we will work with the second one also. So here you can see A2. So we just run, we will do the same work with A2, because here you can see just we need to write now A2 matrix. So A2 matrix will define by this way now. A2, this is 3U, A1, 3U, A1, 1, because here we have symmetric matrix. So we can easily find this A2 now. So by this formula. So, and now we will just run this situation. So this selection, run selection. And now here you can see next conditioning number A2. This is converges. This is not ill conditioned. This is well conditioned problem. You can see this is 1. If K conditioning number is 1, it is well conditioned problem or close to 1. Yes. If it is so far from 1, it is ill conditioned. So here you can see now normalized M2 also. So however, this problem is well conditioned. So the eigenvalues are affected by errors of same order magnitude of the error linked to the perturbated matrix. If we have, so it means they are directly proportional, errors of eigenvalues and errors of perturbated matrix. If we do small changes in perturbated matrix, small perturbation in matrix, we have small errors in our eigenvalues. And now here you can see new graph. So they are very close. Do you understand me? So here you can see they are very close, our eigenvalues and the new eigenvalues, perturbated matrix. Is it clear? Any questions, please? No questions, students? No questions. Okay, so now we'll continue. So this is, it was first exercise from exercise session 4. Here I showed already this just particular situation for n is 5. You can see we get this kind of matrix, our matrix similar with A1. So now let's move to the next exercise. So exercise number 2. Implement power iteration method using a function called power it. So we need to create this kind of function in our editor and fix the maximum number of iteration m max to be executed and relative precision tol. So here we have input tol, it's given value, it's 10 to the power of minus 10. And starting from the vector z, using this tolerance tol, find the eigenvalue of largest modules of the following matrices. We need to find the eigenvalues of largest modules. So, and then after finding, using this power it, so iteration method, power iteration method we will use, and then we will just verify our result with the command egg. So we use power it function and then compare with command egg results. Okay, so now here you can see this power it function, how to build this power it function. So there are inputs A, matrix Z, vector, tolerance, and maximum value for m iteration. This is steps of iterations till m. So we will normalize here Z vector. So, and we denote it with W. W is equals to Z over norm of Z. And as initial lambda, we will consider 0. And here we will consider our loop. So m from 1 till this m maximum value of m. So Z is equals to A times W. So this W, it is normalized at Z. You can see Z over norm of Z. Normalizing process, it's called. So now we'll find our lambda by this formula, lambda m plus 1. It will be W transpose times Z. So this is power iteration method, which we considered in our previous lectures. So then again, you can see here, we will add this normalizing process here and consider stop criterion. Stop criterion if absolute value of lambda m plus 1 minus lambda m is less than any tolerance. So here you can see tolerance of absolute value lambda m plus 1. So what does it mean? Just a second. So here it means, so we need to continue our process till our this tolerance. Yes, it should be less than or equal our tol.
Recording in progress.
Sorry. So here, so first of all, you can see here lambda m plus 1. So lambda m plus 1 and minus lambda m. So the difference between two neighbor lambda and over this absolute value here and absolute value of lambda m plus 1. And it should be less than or equal any our tol. So we will continue this process. You can see till our tol. Okay, so, and now you can see here, it's continuous till this tol. And close this stop criterion and close our loop. Okay, and now, so let's continue and now consider these three matrices. So here we have the solution of this exercise, you can see, and now we will give the maximum value for m max, so it's 100, and the value for tol, tolerance, and z matrix. You can see this is 1, 2, 3. It's not row matrix, it's column vector. It's column vector because of here you can see it will be just like this: 1, 1, sorry, 1, 2, 3. This kind of matrix. This is Z matrix. This is Z matrix. So it is Z, and here you can see A1 matrix given A1, and then using this power it function. Now here in this row here you can see power it, this previous power it function. We will first of all run this function and then run our solution. So here it depends on A1, Z, tolerance, and M maximum. And then draw the graph plot for 1 till M1 plus 1. So in this case, M1, this is output for M max. So you can see it is 100, not 100. We need to continue this process till M1 in this case. Do you understand me? Here, M1. So, and then lambda 1 and B plus minus. It means blue line with pluses. So we denote with pluses our eigenvalues. And here lambda max. So it is lambda 1 till the last component. And here we will use comment egg to check. So eigenvalues A1 egg we denote by this notation, and here you can see just egg of A1, find A1. So eigenvalues of A1. So we just find eigenvalues till here with the power iteration method, and in this case we will find using comment egg. Is it clear? So now let's just run this program, and then it will be more clear. So first of all, we will run this part, this power it function, because we will use this function then. So just run it and then run first part of our exercise. So here we just again run this exercise, and in this your comment window, you can obtain your result. So you can see here lambda 1 now equals to this kind of here we have corresponding values of eigenvalues, and here you can see W1, it is normalized vector, so our eigenvector here, and N1 is 35. So it means we need to continue our process till 35. We have maximum value 100, but when we do 35 steps, it will be less than or equal to. After 35 steps, we have a value which is greater than our total. So we need to continue this process till total and value of total. And now here you can see lambda max. So maximum value for lambda, in this case, it is 2. And then eigenvalues here, you can see eigenvalue using for comment egg. You can see here we obtain this kind of eigenvalues for our matrix through eigenvalues. Here just we will do iteration method and find this is eigenvectors. They are eigenvectors, and just find here eigenvalue. It is 2 by power it function. So now let's consider now graph here. So you can see we have now 35 this kind of values with pluses. You can see in blue line with pluses, we denoted it. If you count here, we have 36 in this case, 36, because the initial value is 0. Is it clear? So this is graph of this function. And now we will do the same work with second A2. So here also written, it reached the tolerance in 35 iteration. And this method converts quickly because the speed depends on the ratio lambda 2 over lambda 1 in a norm. And now let's just run this part for the A2, run selection. And here you can see new values. So here you have m is 100. Here we will continue this process till 100, till the last maximum value, and then lambda max. So from this situation, we obtain from this method, we obtain eigenvalue is equals to 1.9911. This is maximum acceptable eigenvalue. And here you can see with the command ig, we'll obtain this kind of eigenvalues. So here we obtain 2, so they are close, but not same. We have some errors, small errors here between them. So this is last component here, you can see, and we need to take it is as eigenvalue here using this method. And this is eigenvector, corresponding eigenvector. Is it clear? So now you can see here new graph now. So they are very close. We have 100 values for each step. And 101 values, and we have 100 steps here. So now, so this method for this A2 slowly converts, because lambda 2 over lambda 1 here equals to, here you can see lambda 2 over lambda 1, yes, 2 over this one. 1.9 over 2, and it's equals to 0.95. So it is converts slowly, less than 1 here. Okay, is it clear? Now we'll move to the next 1A3. For A3, let's define it. So let's run this program. And now, sorry, I didn't do A3. And now it's correct. So here you can see now, this here again, we have 100 steps, and eigenvalue by this method is equals to 0. This number 2. And but here when we find eigenvalues with using ig, here you can see this kind of numbers. So complex numbers, yes, not real, complex numbers. So what does it mean? So it means it doesn't converge because there are 2 different maximum modulus eigenvalues. So here you can see we have 2 different maximum value eigenvalues. Maximum. So here, module of this number is equals to. There are different kind of numbers. You can see conjugated numbers, pairs. So, and now let's continue and move to the next exercise. So exercise number 3, and now we need to implement power iteration method without vector normalization using function called power it no norm, and do the same work. So for A2 matrix now, and maximum value of M here is 500, 800, and 1100. So we just define this corresponding eigenvector of matrix A2, corresponding, determine the eigenvalue of largest modules, and the corresponding eigenvector of matrix A2 of this A2 matrix. So starting from Z, it is this one, and using tolerance. This is starting from vector Z, 1, 2, 3. Okay, now let's continue. So let me clear second exercise. Okay, now we will use here you can see in power it function, we use it normalizing process. Here W equals to Z over norm of Z. And now we will do it without normalization. Here you can see new function now, power it no norm, which we told about it. And you can see here just W is equals to Z without normalizing. And do the same work here. M is from 1 till M max, and the Z is A times 2W, and lambda we need to find by this way. And W is equals to Z, and again we will return to a M. Okay, so this is new function now. Let's run this function. Sorry, we need to run selection. And then here you can see now the solution of this exercise. So here we give Z function. Here we have a matrix, and let's do it for this one. So 500, 800, and 1100. But here Z is not this one. So 1, 2, 3. And now we have Z vector, we have a matrix, and using this power it no norm function, we define our eigenvector, W, corresponding eigenvector. Let's run this program. And then, so in this previous exercise, we have this kind of graph. It doesn't converge. Okay, now here you can see W. Or we can do just 1, 1, 1, because here we have just equating W with Z also. In this power it no norm function. Okay, so now here you can see now this answer. This is eigenvector, corresponding eigenvector. It equals to this kind of values. It takes this, get this kind of values, our eigenvector. Is it clear? So we used here power it no norm function. So it means using power iteration method without normalizing. Without normalizing. Any questions here? No questions? Okay, now let's continue. So now here, next exercise number 4, implement the inverse power method using a function called inf power it. So it is modified algorithm for power it function, and apply this inf power it in order to find the eigenvalue closest to P, which is equals to 0.5 of the following matrices, A1, A2, and A3. And then use Matlab function eigs here you can see, not eigs, and comment the result from inf power it. Eigs function, it will find all eigenvalues here, all corresponding eigenvalues. And now let's continue. So here we can see now this inf power it function, inverse power iteration method. And then, so let me clear here first of all. So inf power it function. So here you can see outputs are lambda P, W, and M. So, and the inputs are a vector, P is 0.5, and Z vector, a matrix, P value, Z vector, tolerance, value here and the maximum value for M. So here you can see the size. We need first of all give a size of our matrix A, and this is size of A, and then normalize our vector, eigenvector W. It's and we denote by W, so it is Z over norm of Z. And here we need to find lambda P, so which is equals to P, and use LU factorization. So LUP, LUA minus P times IE. So IE, it means identity matrix with same size with a matrix. So then here we have value for M, finding Y, and finding finding solution Z in this case. Yes, Z is here, it is solution U minus 1 times Y, and lambda. So to find lambda, next lambda, M plus 1, it depends on M. It will be P plus 1 over W transpose times Z. And then normalizing our W again. And the open stop criterion. Here again, you can see lambda M plus 1 minus lambda M over lambda M plus 1 in absolute value less than or equal to. And close the loop. Is it clear? So by this way, we can define our inf power it function. So let's just run this program again. Run it. And then let's consider solution of exercise number 4. So here we have again M max, it is 100. We have value of tolerance. We have Z vector. We have P, which equals to 0.5. And we have A1 matrix. And then using this inf power it function, plot the graph. So plot the graph of eigenvalues. Here you can see, again, we will denote it blue line with pluses. And find eigenvalues. It's equals to lambda 1 to last component. And eigenvalues A1, X all. So here we will use this command X. It will find eigenvalues of all eigenvalues of A1. Here you can see A1 and the third component here, and here we can see P. So it means close to 1, close to P, not 1, close to P. Eigenvalues which is close to P. So now let's run this part. So here you can see now lambda 1, value of lambda 1. So and M here 22, we need to continue till 22, this process. And here we can see eigenvector, corresponding eigenvector, and the eigenvalue P is 1. So which is closest to 0.5. So eigenvalue P, we will select eigenvalue which is close to P. P here is 0.5. It's given value. And now finding eigenvalues using X. So here we can find eigenvalues as 3, 2, 1. And here also the closest one is 1. Closest to 0.5, it is 1. So by this way, we will define what eigenvalues which is closest to 0.5. What should we find? Using this inf power it and the X. So now let's again continuous process. So here you can see inverse power measure converts to the eigenvalue 1, the closest to P. And now we'll work with A2. So let's run A2, this selection. So here you can see, so matrix singular to mesh in position. So and I think determinant here is 0 or very close to 0. That's why it's singular. When it's singular, when its determinant is 0. Okay, so here we have lambda 2. And how many operations we need to do here? Just 4 operations here, 4 steps, iterations. And then we'll find the corresponding eigenvector, W2, and the eigenvalue P, which is closest to our P. But when we find using AX command, here we can see 3, 2, and 0.5. So 0.5 is also eigenvalue for our matrix. In our case, we need to find the closest eigenvalue to 0.5. So what does it mean? It means here this method doesn't converge because P 0.5 is an eigenvalue. So here you can see the graph also. So by this graph, you can find, so 0.5 is also eigenvalue for our function, for our matrix, sorry. And now let's run for A3. So run selection. And now let's consider this A3 now. So here you can see 100 steps we need to do here. And here you can see corresponding eigenvector and M here 100 and eigenvalue, which is closest to 0.5. It's equals to minus 2.4737. And here you can see using this command AX, we obtain this kind of eigenvalues, 3, 1, and 0. So which one is closest to 0.5? Both of them. They are equidistant from 0.5. Here also our method doesn't converge because P 0.5 is equidistant from eigenvalues 0 and 1 of matrix A3. That's why it doesn't converge. Is it clear? Any questions now? Let me open comment window. Editor. Can give your questions. No questions? No questions. Okay, so let's now continue and so consider next exercise number 5 here. Just a second. Okay, so let's continue. Exercise number 5. find and appropriate P for computing the eigenvalue of maximum modulus of the matrix A. You can see matrix A by means of Gershgorin circles properties. Do you remember Gershgorin circles? And now we will use these Gershgorin circles. Let me recall one more time this Gershgorin circles. So let me open this file with Gershgorin circles, and I will explain one more time. Just a second. So, okay, let me share now. So here you can see this Gershgorin circles. This one is Gershgorin row circle, if you remember. There was, these ones are eigenvalues, you can see, and all eigenvalues belong to this set. And how to find here? So you can see here 30, this point, and 15 here, and they are eigenvalues in black. So, and then here we have 1, 2, 3. We will just add this row 1, 2, 3 elements, so it is 6, and the radius will be 6. And next in absolute value, of course, the next one 4 minus 4 in absolute is 4, 4 plus 4 plus 2, this is 10, so it will be circle with radius 10, and so on. So we will do by rows, or this one by columns also. So if we do by columns, here you can see 4, 1, 3, it will be 8. So here we have 8 radius in this circle. So it was Gershgorin circles, and now we will use this method to find this Gershgorin circles properties here for computing eigenvalues. Okay, now let's firstly here you can see now this solution of this exercise. So you can see here Gershgorin A, this is Gershgorin circle. Here we will find this Gershgorin circle. So it is equals to, Gershgorin circle we will obtain by this way. So N is size A1 for the first component row Gershgorin circle we will do. Row circle, and figure 1, so center, it will be diagonal elements of A, because you can see here also it will be diagonal elements, our centers. And then so let me just clear here first of all, and then you can see radius row, it is sum of this absolute value minus diagonal element. So absolute value of all elements of row minus this diagonal element. And then we have the sum of absolute values of all elements except diagonal element. So this is Gershgorin circle, and theta, this is just defining our radius. So domain here, yes, from 0.2 till pi, and so on. And consider loop. So, and by this way, we can find what? We can find just our circle. So it will be center plus radius rho times cosinus theta, or so here you can see 0 and 2 pi, not 0.2 and pi, 0 and 2 pi here. The arguments of Line space, it is 0 and 2 pi, because we will define circle in this interval, yes? So, and then here you can see this definition of Gershgorin circle, or we can do it with column circle also, figure 2. Here you can see by column circle. So and now let's select this function and run program. So with patch, we will draw the graph R in red. So we do it, and then return to solution. Here we will use now a matrix, and we will use the property of Gershgorin for a matrix. So from property of Gershgorin matrix, we can say Gershgorin rows, Gershgorin circles, we can say that there is only one eigenvalue with largest modulus that belongs to the circle centered at 5 with radius of 1. Here M maximum value is 1000, and let's run this program, and then I will explain. So you can see here just part of our Gershgorin circles in this case, yes, from 0 till, let me one more time show it. You can see this is part of our Gershgorin circles here. So the first part, it is just Gershgorin A, and here it will just find these circles. And then in this next part, it is just finding elapsed time with tick and tock, you can see. So using power it function and inf power it function. So we already run this program. So this function, that's why it works. If you do not do it, if you didn't run these programs, you need to one more time run these programs, and then run this solution. So here you can see this row Gershgorin circle. Okay, any questions? So we'll continue next time, and it will be the last exercise session. So you can see our practice and lectures in Didactica portal also. If you have any questions, you can give your questions. If no questions, we will finish today's practice. Thank you for your attention. The next time we'll continue. Bye.